Okay, this is a part 2 of the lecture on Green's theorem, and this is a proof part. To make this proof simple and straightforward, we assume the curve we're looking at can be decomposed in this fashion. Over the x-axis, left edge point is x equals a, and far to the right, x equals b is the maximum point over which there's some point involved of this curve is involved. Like I said in the part 1, this over at x equals b can be vertical edge. So for example, like this, now I'm ready, the pen's ready. So over x-axis, x value x equals b, the curve can be like this, like a vertical edge, and there's a gamma 1 going this way and the gamma 2 going that way, and then there's another vertical edge, or it can close up like that. So following argument still holds on this type of thing as well. So with that, also wanted to write that part. So we wrote the vector field F as a component P and component Q. So if you state this integral that is in this differential form notation, whenever you have a parameterization, we have this one kicking in. Let me go ahead and delete that part. And q dy. So this is like a parameterization ready. So whenever you switch to dt integral, this is going to change to dx over dt. That part here is going to change to dy over dt. So line integral can be written like this, and that's a standard notation. So here's a further decomposition. We have two parts, the dx and p dx and q dy separated. Also, we look at the curve and separate into two parts. So each of them, gamma 2, which is the top curve, and gamma 1, which is the bottom curve. So we can all separate it. So whenever you switch this one to dt integral using this parameterization, then it's going to be dx dt here, dy dt. Right, so we're not going to use any general parameterization. The reason we decompose it over x-axis is that x is our parameter. So if you look at the top curve in there, the parameterization parameter is x. So usually we write x equals t squared or something like that. But here, x is going to be x. And y is going to be parameterized in terms of x. So let me explain it once again. X and y's are usually parameterized in this line integral. So let's say there was a t plus 2, and this is a t squared plus 2. That's, you recognize as a parameterization. But let's look at this extreme case, x being t and y being just t squared plus 2. In that case, not much is going on in terms of, for that x, the parameter, usual choice of letter t is actually x. So that's what's going on in here. Given x, there's a y value that's directly parameterized like this. So we can just stick to x and write y as in terms of x, and recognize x can be the parameter of the parameterization of a curve. So parameterization that kicks in here, dx is already dt because that's our main parameter here. In the next part, I focus only on the integral of these two parts. Integral of that part is quite similar. I'm just going to explain that. So let's look at this one and switch to usual integral, not this differential form integral, a usual one variable integral. Our parameter is x, therefore x goes from a to b, that's usually the thing, but strange things going on is gamma 2 is because gamma 2 is oriented this way. It starts from b and going to a, so you can write it as b and a in there. And if you're not comfortable with this way of parameterizing, you can go back and really parameterize it t when t equals, for example, 0, that hits this one. When t equals 1, that t arrives at a. You can do it that way, but you will soon realize that this is a convenient way. So x is going from b to a, so wrote b to a, reflecting this orientation. And p is a two-variable scalar function, is only x component of the vector field. So x is the parameter, and y is parameterized by this formula f2x. So that line integral, one important piece of line integral translates to one variable integral like that. For gamma 1, that curve starts from A to the B, so it's the usual orientation for x. So we will write it absolutely from A to B, but y part is going through a different parameterization, right? Even though we can theoretically think of it as one parameterization, for integral purpose, you need two different formula. You need the formula is over x, it is separated. If you think about it, of course you want to switch this one back to A and B. If you put back to an A and B, and that's going to be negative sign. And knowing that F2 is in top and bottom, now we have A and B dx and A and B dx, and you can bring that into the single integral, and that's what I'm doing in the next part. But I didn't write negative p there. I pull out the negative outside, so I have this positive inside the integral, f2, that gets the upper part, and because this was positive, pull out the negative, it becomes negative there. So if you focus on that one, that's how this first two terms simplifies. It's a single integral, one variable integral a to b, and p of x in f2 minus p of x f1. f2 is a function of x, f1 is a function of x. Now, next key thing is that you realize that this is one of the things you go through when you do the iterated integral. So what we are about to do is kind of reverse the process of iterated integral so that you turn that into one variable integral into iterated integral. From iterated integral, we switch to double integral. That's where the direction we're going. So think about that. This is something you got obtained from iterated integral. X is fixed and y is changing. So that must have come from y integral. That's something you can think, make a connection to it. So it's a key part here is recognizing this as an iterated integral. So this is another interesting reverse part we're talking about. So look at it here. That looks a lot like you plug in y equals f2, y equals f1, and subtract it. That's something you get when you evaluate antiderivatives, one variable integral. So here it is. There is some function you have to figure out, such as if you plug in f2, f1, you get this one. Think about it. That's precisely just that f of xy. So x is fixed, and you plug in y equals f2, that part, and minus that part in there. So that is even closer to what you get right before the iterated integral. And think about what is that, how you can kind of think about reversing this. What would have been the earliest step, before you integrate? This is after you integrate, right? So what's the reverse part? Is differentiation. So to put this one back into the iterated integral, you actually have to differentiate. But this is all about y. Plug in y value. This must have been differentiated with respect to y to get inside the iterated integral. Then integrate with respect to y, then you go back in here, right? So to get here, it was integrated. How do we go back inside the iterated integral? You have to differentiate it with respect to y. So here's the answer. This bracket operator, which I call in my course, and differentiated going inside the iterated integral, you have to differentiate it with respect to y, and that's dy integral, and boundary, so exactly f2x and f1x. That goes inside like that. So this is going to be repeated 3 more times, carefully looking at the sign is which sign is correct and things like that. But this is the key moment where you switches from line integral to double integral. If you think about it, on one level, you have to understand this technicality and each step mathematically be able to justify. But it's quite exciting, interesting to see the very moment when it switches from line integral to double integral, when the magic really happens. It's just like a backstage of the magic stage. You probably have practiced these changing iterated integral to double integral, but let's think about this one again. Once again, given x in between a and b, y is varying from bottom f1x to all the way up top to f2x. This is a graph of, this is the wrong thing. Let me go ahead and fix it. All right, doesn't seem I prepared the slide, so here it is, sketching it there. This was the curve. Forget about orientation because iterated integral and double integral orientation wasn't very important there. So this is a top curve. That's this is y equals f2x. Given x in between a and b, bottom curve is this y equals f1x. And given x value, y value changes from bottom f1x all the way up to f2x, and that's what this one is indicating right there. So integrating like this, and I hope you recognize that this is precisely the iterated integral version of the double integral over this region D. So that one over there must be equal to double integral of D integrating this function py, this time switching to double integral part dx dy, not iterated integral. So there it is. That's why that part over there switches to double integral. So this is the most interesting, exciting part. You're witnessing exactly where the line integral magically turn into double integral. Now going back to the original problem, this picture is about Q integral. So we forget about that part for at the moment. So I blocked it. So this is the original integral. We just took care of all the P integral part, realized that that's actually double integral over D, Py with a negative outside, the dx dy. Negative was caused by this direction top curve giving in the wrong direction. It came from there. So next part is this Q integral from C to D and D to C. That really involves this picture. Let's go ahead and see this picture there. If you look at y part, the other breakdown of the curve, this is the top curve, G2, from the relative to y-axis, and this is actually rising, so it is in the opposite situation. This top curve, or rightmost curve, is in the correct direction. It's increasing y value direction. The other bottom is backward. So if you look at this integral, which is y value going from C to D, if I label that bottom y value C, top y value D, this part is going along the G2 is going from C to D. Integrating Q, given y value, X is changing along all that thing. I said wrong thing, along all that thing. X coordinate is given by this function parameterization G2y, and y is the main parameter this time. The other one starts from D to C, so it's D's bottom there, and C is in the top. And as we switch this one so that this two integral have the same order of limits, then it becomes a negative, and then we have the following thing. I hope it's not too small. Q2y is copied. Now C and D is the same as we put the negative sign in there. So this is QG2y minus QG1y. Again, this is where it switches to. You can change that into iterated integral like before. So I wrote it down here. This part, Q2y minus QG2y minus QG1y, is denoted like this. That's exactly the notation that representing that. Now, to go back to the integral, you have to differentiate this one with respect to x, because that's the x value we're plugging in there. And that's why you see down here, this one going inside as a q partial derivative with respect to x. The limit is q1 and g1 and g2 there. Okay, so like before, if you think about it, any given value in between c and d, x is varying from g1 to g2. That's precisely this iterated integral. It's precisely the double integral over d with this function qx. So here's at the end, we just took care of the second two terms. That's double integral and double integral over the same region D. Inside together is a qx minus py, and we recognize this qx minus py is not some, exotic expression. It is some phenomena that the structure generalized to higher dimensional or more general situation. So that was the proof for the case where the curve is broken into pieces, parameterized nicely like that. Even though it is not, don't want to make any general statement, it takes a lot of work to describe all sorts of different shapes. So I'm just going to look at some simple examples to convince you that you can do following thing. Then you can break this more complex cases into these simpler cases like that. Right here is some arbitrarily, but actually in fact more carefully so that I don't have to do too much work, is a picture. So if you think about breaking this one into these pieces, top part, you can see this doesn't pass the vertical line test. And the bottom part, if you look at this as a bottom part, that bottom part doesn't pass the vertical line test and things like that. So though, if you want to look at this as a two pieces over x-axis, vertical line test is a problem to look at as a two pieces. So see where those vertical tangent lines are. So for example, go ahead and of course that's the left endpoint in there, but if you look at it here, that's one vertical line part. That's where it splits. So maybe I'm going to go over there like this, and that's another vertical line part in there. I'm going to go ahead and change that part a little bit simpler so that I don't have to do anything too crazy. So maybe I'm going to do it like that. Then, and there's this vertical line there. I realized another one there, like this one in there, vertical line. So these vertical lines kind of give us some idea to how to break these curve into pieces. For example, all right, if I look at, you don't have to look at it like this. If you look at this part in here, let me use a different color. Look at it here. Try to make it as big as possible so that you don't have to do a whole lot of work. So I'm going to call that part piece D1. If you look at that piece D1, that has this left edge. That's the top curve, and that's the bottom curve. So it fit into that category in there. So I forgot this vertical line there. So definitely this will be here. Another piece there. That one itself will satisfy that. And if you go extend it there, then it seems like this piece over here is going to satisfy D2 and D3, something like this. So in the middle part here is D4, definitely that has a top and bottom. Every top piece and bottom piece passing vertical line test. And this one here is a D5, something like this. So I could divide this one into 5 different pieces so that we have this top and bottom pieces in there. Each of them, by looking at each of them, you have to make sure that passes horizontal part as well, so that which I forgot to do. So now this you have to draw, by looking at each pieces, you have to draw like a horizontal piece and see if that passes. It seems like it does pass the top and bottom part in there. Is that true? Maybe I have to divide it into 4 other pieces like that. Let me think about it a little bit. Yes, T1 works. Make sure that you have to, when you draw a horizontal line, it doesn't pass through 2 parts of the curve. I mean, more than 2 parts of the curve. It starts in there and ending it there. This one looks okay. D3 is a problem, I think. You have to divide it here further. If you draw that line, horizontal line, you can see that passes through several things. So draw this horizontal tangent line, and that helps you to dividing this one. So D3 should be divided into D3-1 and D3-2, D3-3, like that. I guess. And D4 looks okay. Top and bottom is divided. And in my opinion, it looks okay now. I think even this one, I mean, if you start from there, even though that formula is different, just theoretically, it all works there. Now, you can do whole thing. This is the thing that we can write this D, write into call it D, this entire curve, the boundary curve, as a sum of all this thing D1, and there's a D2, and there's this D3-1 and D3-2 and D3-3 plus D4 and plus D5. And at this point, I want you to look at this plus symbol as a union. It's not really adding two numbers and anything like that. So we're putting this one together. So what that means is if you're going over line integral D, you go over line integral D1, and then really add the number, the value of line integral over D2. That's what I mean by this sum. All right. Then it's going to be the same as the line integral over D. That has to be explained. If you look at this D1 is oriented this way, oriented that way. So if you look at this region D1, you can see this orientation we have originally from the boundary curve. So as you go around, the region is on the left side. Now, if you look at look at this part, continuing this orientation, you have to go around like that, so that it's on the left side. Now, this boundary happened to be boundary of this D4 as well. So D4, I'm going to close it up here. D4 is getting really messy, apologize. So because the D4, how would you orient to D4? It's coming from the bottom part, which is the original part of the boundary. That has to be left side region. So it going around like that. It continues, go around and go around like that. As you can see, this boundary always have two regions, small enough boundary, one to the one side and the other side. And you can see, because if you switch the side and the other one is the one direction, it's going to be the left side. The other one has to be opposite direction on the left side. So if you happen to have certain boundary and this is the region, for that region, it must be on the left side, is oriented this way. The boundary is going this way. But if there is the other region on that side, for that one, boundary on the left side, so it must be going that way. So if you integrate this part for that region, then it's going this way. For that region, going that way. It's exactly the same path in a different direction, so it's supposed to cancel each other. So this part was additional, wasn't really part of the original boundary of this curve, canceled out as we further divide into different pieces and individually integrate over these kind of closed loop, and eventually all the middle parts cancel out, giving you only the boundary part left out. So justify that it's going to be the same as the boundary. Now, this is one shape. I already had a little trouble with how to dissect it in there. Now, if somebody says that, how about all the general shape, and how are you going to provide the general strategy of dividing it like this so that it always works? You can imagine that's a lot of work. That's why I didn't go into that area, and you have to put a lot of condition on that curve so that this can be done. So it looks quite messy and requires a lot of description, I think. So, but if you just assume the simple condition and focus on how this integral switches to from line integral to double integral, and that's the part I think we have to focus on. But in itself, thinking about all the possible curves and how to divvy that up so that we can use this basic result to the more general result, and in itself is an interesting question. So that's it for the Green's theorem.